of people that are joining us from all over Nova Scotia this evening, and it's really nice to see them. I would like to begin by acknowledging that we are in Mi'kma'ki, the traditional territory of the Mi'kmaq people. I also want to acknowledge that the African descent people have been in Nova Scotia for over 400 years, and we honor and offer gratitude to those ancestors of African descent who came to this land as well. I would like to introduce our first seminar speaker for our series this year. Mr. Baechler is EXP Services Chief Hydrogeologist and Senior Surface Water Hydrologist based at the Sydney office. He has more than 50 years of experience, primarily here in Cape Breton, but he's also had experience throughout Atlantic Canada, as well as overseas assignments in Southeast Asia, Europe, and Mexico. During this time, he has addressed climate change and impacts to freshwater resources as a regulator, Nova Scotia Environment, consultant, researcher, and educator. He is also an adjunct professor at Cape Breton University. He has been undertaking research on Cape Breton's changing climate and the impact of freshwater resources for over 25 years, and we are delighted for him to be speaking with us this evening. Over to you, Fred.
Good evening, everybody. Thank you very much for joining in. Next 40 minutes or so, we're going to talk about the impact of Cape Breton's changing climate on its freshwater resources. Now, we are going to get into some of the practical details of what I've found, but I've also found that over 20 years of working on this, at times you have to stand back and see the forest before you get down into the trees. So during the talk, I'm going to hit you with two overriding concepts. There's no easy answer for these. I just want to make you start thinking about things related to climate change that maybe you've never even thought about before. And slide won't move. So it's stuck. The technology of it all.
Brett, I think there might be some. I think there might be people online that aren't muted.
Oh.
Yeah, there's a lot of
thundery sound.
background noise here.
Just click on this button.
Okay, so this doesn't work.
Yeah, seems like it will be on the page.
Okay. All righty, folks. So we're going to hit you with the first overriding concept right off the bat. And this is probably best. Still not working.
This arrow right.
Okay.
Okay, sorry.
The fun and games of it all. Okay, so the first overriding concept I want to hit you with is probably best identified by Dr. Bernard Murphy from St. Francis Xavier University, who said the pace of change is like a song. You need to understand the natural beats and rhythms of our planet before we can detect a skip in the beat created by humanity. Now that sounds like a mouthful. See if we can help you understand that. So this is a temperature profile that's been gathered together from the NOAA, the National Oceanic and Atmospheric Administration in the US. They pulled together all the data on the world's temperature, starting at about 60 million years ago over on the far left side of the slide, down to present on the right side of the slide. So you can see there are a lot of natural rhythms and beats to our planet. Back around 55 million years ago, it's called a thermal maximum, 5 to 8 degrees centigrade warmer than now. No polar ice caps, rainforests in the Arctic, created by a massive greenhouse gas injection from volcanic activity. And then temperatures started to decline, a different natural rhythm and beat. Ice started to form at the poles about 35 million years ago. And then they just continued to decline with another set of natural rhythms and beats till around 2 million years ago. And that's when the bottom fell out of her. We went into the ice age that we are in right now. For the last million years, for the first part of that last million years, we had cycles of ice movement about every 41,000 years. And in the last little while, we've had 4 major ice advances every 100,000 years. Different natural rhythm and beat to our planet. Then we came out of the last ice age. Up till about 10,000 years ago, looked like we were climbing right back up to another interglacial period. And then it just flatlined. Entirely different natural rhythm and beat. Why? No one's quite sure that I've been able to understand. If you want to look at humanity and how we transition through these natural rhythms and beats, well, from about 7 to 2 million years ago, we transitioned from apes to hominoids. 2 to 3 million years ago, we went into hunter-gatherer society. And our immediate relatives, Homo sapiens, started about 200,000 to 300,000 years ago. So we've transitioned through quite a lot of natural rhythms and beats of our planet. We take a look at that last period in there where we climbed out of the last ice age. We look at the temperature profile. Well, we started low, we came out, there's that big peak at about 15,000, and then for 1,000 years, we dropped right back down to an ice age, which hasn't happened before in the previous glacial events. And we climbed back out of it. Ice left Cape Breton about 10,000 years ago. And from 10,000 to present, that's called the Holocene warm period. Started about 10,000 years ago and pretty much flatlined compared to the rhythms and beats you saw before, but there's still all sorts of small fluctuations in there. But interestingly enough, for humanity, this is where our whole civilization began. Agricultural era was there, irrigation era, engineering era, and the Industrial Revolution. So as a human species, it's been that last 10,000 years that we've been pretty lucky where temperatures pretty much flatlined. That's the natural rhythm and beat that we're used to. So given that, the question for you is, so what do we want to return to? We hear so much about climate change and saying that if we can only solve the greenhouse gas emission thing, we'll be right back to where we are. Well, really? So where do we want to go back to? Do we want to go back to that last 6,000 years or 10,000 years where we're flatlined, but no one's really sure why that anomaly is there? We should have been going up higher in temperature to come out of the last ice age. Well, if we wanted to go up 2 degrees, that would take us to about where we were during the last interglacial, 125,000 years ago. Do we want to go there? Or would we sink right back into the next ice age? If we go further back in time, the last time we were at plus 2 degrees was somewhere around 4 million years ago. So really, do we want to go back there? It took the planet 4 million years to get to where we are now, and we're going to go up there in 100 years? It's exactly who's going to be able to adapt to that. Or you might hear some people say, well, gee, if we go back to where we were, you know, if we can't handle the greenhouse gas and we go up to 5 to 8 degrees centigrade, then we might get way up to that spot. You know, tropics in the Arctic, maybe that's where we'd like to go. But just keep in mind, there have been 6 global mass extinction events. That was the 6th one. Do we want to go back there? So that's an interesting question. So the second part of this issue is how do freshwaters respond? So that graph I showed you is just of temperature. But for the work I'm doing, I also need to know what precipitation did during that period. And this I really had to wrap my head around. Because if we think of natural rhythms and beats, let's say we had the sheet music for a major classical symphony. And those are all the natural rhythm and beats of our planet. But in Cape Breton, we can only go back 100 years where I can see temperature and rainfall. So it's though I had all that sheet music, but all I could see were the last 2 bars. That's all I can work with and see what changes are going on. So in there, I might see, well, it started off at 4/4 time, then it changed to 3/4 time, then 7/8 time, and there are a whole bunch of 30-second notes in there rather than half notes. So I can start to see changes, but I don't know whether that's a natural change that's happened to the previous sheet music, or is this something new that's going on? So when I talk about the things I'm going to discuss in the rest of the talk, you just have to keep that in mind. I can see change, whether it's been there before, whether it's something new. That's something that's a little bit more difficult to get a handle on. And just to bring it out front right off the bat, yes, I do believe that humanity is causing changes in our climate, but I also believe that Mother Nature is doing a pretty good job on impacting as well. That's why you'll hear me talk about changing climate, not climate change. Okay, so this is our table of contents slide. So those of you in Cape Breton, where is this? Any idea? Oh, I stumped them the first time out. Okay,
That's
this is under.
Margery Island.
Pardon?
That's Margery Island in the.
Very good. Ooh, very good. So this is on a good storm event at a place called Cap Lemoyne on the west coast of Cape Breton Island, between Margery Harbor and Shuttecamp. And that's Margery Island way off in the background. So we're going to use this as our table of contents slide. And I'm going to go take you through 3 things. 1, we're going to answer the question, how is Cape Breton's climate changing? 2, how are its surface waters changing? 3, how are the groundwater changing? So let's see if we can tackle that first one. How is Cape Breton's climate changing? Now this is the second and last big concept I'm going to hit you with. Because for me, it's really interesting that in terms of climate, right now, we have more satellites, more ground stations, supercomputers, and they are all dumping all of their data in real time to a set of 4 or 5 major climate change models. And that allows them to continuously be updated. And that's when we go on our phone and say, well, you know, what's the weather going to be like tomorrow or the next day? At any point in the globe, they can tell you that. Everything, there's a lot of data, but it's all going into a central area to be analyzed real time. Yeah, that doesn't work so much when you get to water resources. So in terms of Cape Breton, I've found that a lot of this data on our freshwater resources is there, but it's stored in a whole bunch of different spots, which I would call silos. So far over the last 20 years, we've found 36 silos where data can be stored in that is relevant to Cape Breton and that I can possibly use. So question then is, like, if freshwater resources is a big thing for the next coming decades and out to 100 years, why aren't we doing the same for freshwater resources as we do for climate to help us adapt? Climate stations. Here are all the climate stations on Cape Breton. Not only Environment Canada, but there's a Cape Breton Mesonet that probably some of you know about. Nova Scotia Natural Resources have a series of stations that measure parameters noted for forest fire index. They're the highway cams. There's Environment Canada's COCORAS system. A long time ago, they actually looked at precipitation chemistry, but those stations are abandoned. But one of the very fortunate things we have in Cape Breton is we have one of the longer climate stations in the country at Sydney. It started records in 1895 and continuing all the way through. So you probably won't guess where this one is, but this is on Inverness Beach looking out over the Gulf of St. Lawrence and a nice storm cloud coming through. So let's take a look at precipitation that we get. First, I have to introduce you to an idea called the North Atlantic Oscillation, or NAO. So you've all probably heard about El Nino in the Pacific. Well, we've got one in the North Atlantic called NAO. And really, it's a function of atmospheric pressures between the Icelandic low and the Azores high. And that governs where the jet stream lies. And that in turn alters our climate. So they've tracked this, and what they found is in the 1950s, started to get colder. In the 1980s, we started to get warmer just because of where the jet stream was positioned. Keeping that in mind then, here's the precipitation data for Sydney. So that blue line shows if you took the total precipitation every year and plotted it, that's the blue line you'd get. But if you wanted to smooth that out a bit, what I did was to take every 10 years, take an average, then move that 10-year period ahead 1 year, take another average. So it tends to smooth things out. And when I show you some of these lines for some of the other variables, that's what you're going to be seeing. So if we take that line and expand it a bit, this is what we get. So you can see we were coming out of the Little Ice Age, the late 1800s to early 1900s. That nail, yeah, that started to see increased precipitation. And when we got a positive nail, we started getting decreased precipitation. So although precipitation in Sydney is gradually increasing, as the climate change models would suggest, we've got this 20 to 30 year cycle in here, which is not part of that long-term trend, and it's being impacted by what goes on out over the North Atlantic. Now this becomes pretty important if you're a consultant, because if you were in there in the late 1980s at the peak, and someone said, well, so increased precipitation is going to happen, and you started saying, well, it should go higher and higher from that peak, and then all of a sudden the cycle went down, your clients would probably be looking at you saying, huh, what the hell happened there? So yes, we do have long-term increase in precipitation, but we also have this 20 to 30 year cycle going on that we have to account for. Air temperature. Anybody know where this one is? Everybody's looking. So that's Inverness Beach on a nice low tide, looking west. So that's the Mabou Highlands in the background. Now, when we talk about air temperature, introduce you to another concept, the Atlantic Multi-Decadal Oscillation, or AMO. And simply what this means is the temperature of the North Atlantic. And this comes off a graphic you can get on the satellite images from NASA. And the yellows and reds are much warmer than normal. But they've plotted this over time. So you can see in around the 1920s, the ocean started getting warmer. It decreased, it got cooler in the 1960s, then started to get warmer again. So there's this long-term 30, 40, 50 year cycle of what's going on out in the North Atlantic. So if you look at our air temperatures, so this is the mean annual air temperature for Sydney. There it is. The ocean started getting warmer, our air temperature started getting warmer. Cooler, warmer. So again, the North Atlantic is playing a role, and yes, the temperatures are gradually going up, but we still have these decadal scale cycles going on. So to put it in a nutshell, the next time you stand out along the North Atlantic at the Gabarus Wilderness area and you're looking out over the ocean, you may want to keep in mind that it's the air pressure changes that are going on over the ocean, and the temperature of the ocean itself is really having a big control on what's going on with our climate. Snowfall. You probably figure out where this one is. So that's Reserve in the background, New Waterford, Midground, and back to the Cape Breton Highlands in the background there. So here's total annual snowfall every year from Sydney Airport. And again, you're starting to see these cycles, more snow, less snow. So those air pressure differences over the North Atlantic are playing a role in our snow cover. But it's been going down ever since around the 1960s. Gradually getting less and less. Our winters are getting milder and milder. However, that's at the Sydney Airport. And in Cape Breton, we have to recognize we have a series of mountain towers, which are high elevation areas. So the blue is Sydney Airport, where I was just showing you. The yellow is North Mountain, where we're going to take you now. And the reason we're going to go there is that there are microclimates on Cape Breton we have to keep in mind. And the snow belt that sits over the Cape Breton Highland is created by these streamers of wind, nor'easters, and they come across the open Gulf. They pick up moistures. They hit the Cape Breton Highlands. They rise up, they cool down, and the drops it as snow. So it becomes important as to how much ice cover we get over the Gulf of Mexico, the Gulf of St. Lawrence. Now, to give you an idea about that, if I can get this to work. So the panel on your left, you can see the Gulf filled up with ice. So if the Gulf is open and no ice, it gets a chance to pick up moisture, and it can continue to pick up moisture and create the snow melt. But if it gets packed up with ice, as would normally be the case, then that whole system shuts down. The panel on your right shows that in March of 2011, there was no ice in the Gulf, and it's the same thing happened in the past winter. So they've looked at the amount of ice in the Gulf of St. Lawrence, starting back in the 70s, and they found that the amount of ice is getting less and less and less. They think this is because of climate change. So this becomes interesting because in most places of the globe, the glaciers at high elevations are melting and getting less and less. But in Cape Breton, we might have the opposite, because as the Gulf gets warmer, stays open longer, no ice, creates a bigger snow belt in the highlands. So what's the Highland snow belt look like? Well, if you've been up over North Mountain, probably in March or so, this is what it looks like. The depth of snow is shown on the left part of the graph, and the bottom goes from October the 1st to June the 1st. So if I plotted up the amount of snow that was received in Sydney Airport on this particular year, that's what it would show. If you plotted up the snow that was received on North Mountain, that's what you get. So builds up early, no melt events, flat lines at the top because it inundated the snow gauge, and then doesn't really melt till the end of June. So when we're talking snow, we have to remember snow on the lowland is different than snow in the highlands. Okay, sea level rise is really not part of precipitation or temperature, but all too often people think of sea level rise associated with changing climate, so I thought I would throw it in here. I doubt whether you'll know where this is, but it's at Johnstown on the southern part of the Great Bredor, and you're looking across the Great Bredor Lake. This will be our background slide. Now, you may not have known where that is, but anybody know where this one is in Cape Breton? Pardon?
Is it Marble Mountain?
Nope. So this is Bay St. Lawrence. And the reason I'm going to take you there is with all this discussion on sea level rise, all you tend to hear is, oh, the International Panel on Climate Change says we're going to go up by 0.5 meter or 1 meter. Everything is focused on now. But if you remember the concept of natural rhythms and beats, it's really important for us in Cape Breton to recognize we have been through an immense amount of sea level rise and fall. And the reason for going here is this will give you an idea of historical sea level, because 125,000 years ago, sea level was much higher, and it cut the rock and created a platform. And that platform is available to see right there. So if you go to that beach, there's the wave cut terrace. And it shows that sea level back 125,000 years ago was about 5 meters higher than it is right now. After the ice left, sea level, so this is a picture of Cape Breton when sea level was 50 meters below where it is right now, and that was about 9,000 years ago, just after the ice left. So you can see we were not an island. We were joined to the mainland. We were joined with Prince Edward Island, and we were almost joined to the Magdalen Islands. And if you look at the center of what now is Cape Breton, there was no Bredor Lake. 6,000 years ago, yeah, we were still joined with the mainland, but not PEI. And about that time, sea level rose high enough, it started to flood in and flood out the Bredor Lake. You wanted to know what that looked like? So here's a picture of what the Bredor Lake looked like back just before 6,000 years ago, and all it was a small set of freshwater lakes. And I've shown you Waikagama, Badeka, and It was only just to give you an impression of where you're sitting. But after it flooded, this is what it looks like now. So essentially, sea level rise for Cape Breton has flooded out already 1,100 square kilometers of what used to be a freshwater ecosystem, and now turned it into a saline water system. And so now we're faced with a unique situation, and I don't think there are too many other places that have it. We are now getting sea level rise impacts from the outside in along our outer coast. But because the Bordeaux Lakes is now saline, 2/3 the salinity of seawater, we're now getting salt water going from the inside out. So we're getting hit from both sides. Where are we right now? Well, there have been some geological studies done, but the neatest one was Fortress Louisbourg, and they looked at the height over on the left there, the 1743 high water mark versus the 1998 high water mark. So the Fortress Louisbourg actually gave us an idea of what present day rates are, which are about 0.36 meters every 100 years. Here's the tidal record from North Sydney, which is giving us a rise of about 0.2 meters in 31 years. So it's a little bit higher. Okay, so we've gone from the past to the present. What do we see in the future? Well, this is Cape Breton Island with the coast shown. And if we want to know the impacts on seawater rise, we need to know where the people are. That's a little bit difficult unless you plot up all the domestic water wells. So that gives us a good idea to where the people are. So if we see a sea level rise of, for me, if you look at the sea level rise predictions, you add on the natural rate, you add on storm surge, wave height, you could be in the 10 to 15 meter rise. So that would take out everything in yellow. So now we're starting to have some impact on some of those wells, you know, Mont de Mire, especially around Isle Madame, along the southeast coast. But if you remember, I said that would we really want to go back to 55 million years ago when there was no ice at either pole and we had the tropics in the Arctic? Well, the best estimate I've seen is that if we go back that far and all the ice melts, sea level rise would be about 80 meters. So this is what Cape Breton will look like under that. An awful lot of those red dots are gone, and we've gone into one island. We're now into about 10 small islands. So that gives you an idea of the range of what we might look forward to. Okay, so that answers the first question, hopefully for you. How are surface waters changing? I was going to ask you where this was, but yeah, I messed that one up. Okay, so this is what we're also fortunate about in Cape Breton is that we have one of the oldest stream gauging stations in the country. And it's on the Northeast Margaree River, just downstream of where this photograph is taken. And here you're looking upstream, Northeast Margaree, and you're looking into the steep gorge where it's coming out of the Cape Breton Highlands. On a beautiful fall day. First thing we want to do is look at the length of record that we are working with. So with climate, we had 129 years starting in 1895. With stream flow in the Northeast Margaree, we've got 107 years of data starting in 1917. And to their credit, the feds have kept that going. It's continuous record. Also to the federal credit, they started taking water chemical analyses back in 1965. So there's 210 water chemical analyses available. And to Nova Scotia Environment's credit, they put in what's called a hydrolab data logger back in 2002. So we have 22 years of data, and that hydrolab collects hourly information on 5 chemical parameters. So we've got a really nice data set to work with. And as you can see, it's crossing a lot of that big decadal cycle of flow going up or precipitation going up and down. So it gives us a good handle on how things are changing as that moves. So a couple of things we'll look at is the mean annual flow in the stream. Here it is. Again, it's responding to the precipitation, just as we did previously. So we're getting changes. And again, if you're a consultant, you really need to, and you're trying to provide information to a client as to what flows might be, you can say, yeah, flows might be going up because precipitation is going up, but you really have to keep your mind on these decadal cycles. Now comes some interesting things. The timing of winter flow. So what they've done in the Northeast US is they said, well, instead of saying when is the peak stream flow, with winter, the spring melt, what they said is, let's take the whole winter period. We'll calculate how much water is flowing past the gauging station, and we're going to figure out when 50% of that water passed the gauging station. So I thought, well, I'll do the same thing. Now it's a bit of a weird line, but all you have to remember is back in the early 20s, 50% of the flow passed around by the 5th of May. Now it's going past about a month earlier, 10th of April. So mild winters, more intermediate snow melts during the winter months rather than the big peak flow at the end. And again, this is what they found in the Northeast US, which are sort of dealing with the same climate we are. Well, how about the summer flows? Now, in this case, I just looked at what day did the absolute lowest stream flow occur. And what this says is back in the 40s, the lowest stream flow happened in the 12th of September, but now it's backed up to the 13th of August. So almost a month earlier when we're getting these really low flows. But that's not the whole story, because usually what happens is that the stream flows go down, but then they start to climb up with the fall rains. But when you do that, and we looked at this, I took October, November, December and said, which wind does 50% of the flow pass? Came up with this graph, which simply says, back in the 30s, that 50% happened by the 13th of November. Now it doesn't happen till about 2 or 3 weeks after the 25th of November. So when you combine those last two together, it means that the really low stream flow is happening earlier, and that low stream flow is lasting longer before the fall rains kick in and start raising them up. And if you're looking for a good example of that, that's this year. So that's the stream flow in the Northeast Margaree from the beginning of 2024 on the left to yesterday on the right. And you can see we got the big peaks during spring melt, but then it's just gone down and down and down. There are a few little peaks in there from little rainfall events we've had, but we really haven't had an awful lot of rain during the summer. It's been a relatively dry summer, and stream flows are just getting lower and lower and lower. Well, how about peak flows? That's usually something people are interested in. So the blue line is the dots every year, which of the days that record the maximum flow. And over that we can so over that, we can place, this is the mean annual flood, so it's discharge, cubic meters per second on the left. That would be about the mean annual flow. Here's the 10-year flood and the 50-year flood. But for those people living along the edge of a river, it's not about the mean daily flow. In other words, to get that blue line, they had to average all the flows over one day. But if you're living beside the river, it's not sort of the mean daily. They want to know, what's the peak? When is the instantaneous peak? Because that's the one that might cause the damage. So that black line is the instantaneous maximum peaks. So you can see from about the 60s on, we're getting an awful lot more of those big instantaneous peaks coming through. And those are what's causing some of the big damages. So there's something going on with the peak flows. Water temperature. This becomes a big issue, especially in terms of salmonids. So this is the Northeast Margaree at the gauging station, looking downstream. So as I mentioned, Nova Scotia Environment has a hydrolab data logger in it. So once an hour, they record temperature. And this is that temperature graph. So the peaks are summer, the lows are winters. What is interesting here for salmon is that we're gradually getting about a 1 degree centigrade rise. But for salmon, 20 degrees is the cutoff. That's the one that they really have problems with when it gets above that. And so we've had a number of them over the years probably in each year there's a little bit. So I was wondering, are we getting more longer zones above 20 degrees? So I did a little graph. So the blue line shows the percent of time every year that it exceeds. And then the duration of days is the orange line. So that time when it's important for salmonids, where temperatures are exceeding 20, it's getting longer and more often. If you wanted to bring that down to present day, anybody know where this one is? Ooh, everybody's thinking smoke's moving. This is the gauging station on the southwest Marguerite, one of my monitoring stations. And if you went there this year, which I did in July as part of my monitoring run, this is what was posted. Warm water closure in effect. The temperatures had reached so high in the southwest Marguerite that it was closed from July 12th, 2024 through to December the 31st, 2024. So we're bringing it right into this year. Okay, pH of water. This becomes important not only for salmonids, but also for us if we're using surface waters for water supply. But first I have to introduce you to a bit of a concept here, and that's wetlands in Cape Breton. So there are over 14,000 wetlands on the island, which covers about 8% of the island. And they're focused in three big areas: the Cape Breton Highlands, the Eastern Coastal Plain, and the Sydney Basin. So here's an example of some of the massive wetlands up in the Cape Breton Highlands. Anybody know where this one is? You've probably driven right through this scene at some point if you've driven around the Cabot Trail. It's because way off in the background, you'll see the Cabot Trail crossing the river. This is Fishing Cove River up in the Highlands National Park. So we'll use this as our background slide as we go through the next little bit. And the reason that wetlands are so important is that they can dump an awful lot of acidity down the streams. So here's a spring in the middle of one of the wetlands. But during the summer, when we don't get much rain to flush stuff out, it sort of builds up. So you can see iron precipitate, the manganese scum on the surface, iron bacteria in there. There's metals associated with those precipitates. So all that stuff sort of builds up in the summer, and when the first fall rains come, it flushes it all down the system. And so you might be fortunate enough in a lot of rivers, you just get absolutely clean, clear water. But you get those organic coming down, yeah, it just looks like tea that's been sitting on the stove and for about 3 hours. Now, this becomes important for humans because there are some villages in Cape Breton that draw water from these sorts of streams. And when you're trying to get rid of the color, you have to be very careful, because if you don't do it properly, then you get trihalomethanes, which are carcinogenic. So this becomes a big treatment issue for people who are going to draw water from these sorts of rivers. So here's that hydrolab data logger record. They're taking pH once an hour from 2002 to present. Amazing set of data. But if you'll notice, that's pH of 7, so that's neutral. You notice from about 2010 on, we're getting an awful lot more peaks down into the acid range. So I was wondering, yeah, what's causing those? So let's take a look at that particular one. Turns out it's a first fall flush event. So here's the discharge between the 1st of September to the 25th of October. You overlay the pH, you can see every time you get those big fall flush, the pH drops from, the 7 to 7.4 range down to 6.26 range. And then it takes a long while for it to recover. So those first fall flush events are creating this issue, which to my mind would become from these massive organics. But then I was wondering, well, what about that really low one? Well, it turns out not only do we get these big flush events during early fall, but we also get them with the big spring flush events. So this is from the 14th of April to the 15th of May. The blue line is the stream flow. Here's the pH. Same thing. Big changes going on. Now, this is an interesting facet that I've got to keep in the back of my mind when I see this data. So my question is, well, is this due to climate change? Or is it due to the fact that because we're so interested in climate change, we're putting data loggers out there and we're getting more information than we have ever seen before? And maybe that's what this is. Maybe this has been going on all the time. It's just we never had the data sets to see it. So a lot of times in science, at least for me anyway, when I start looking at these big data sets, I'm thinking, that's really neat, but maybe that stuff's been there before and we've just never had a chance to look at it and see it because we haven't been gathering the right amount of data. So it's something you have to keep in the back of your mind when you're doing this sort of research. Okay, that's how surface waters are changing. How about groundwaters? So again, length of record, we looked at climate, 129 years, surface waters, 107 years. But groundwater, we only have 39 years since 1985, but it still takes us through that peak down to a low in terms of precipitation. So there may be something in there we can work with. Anybody know where this one is? Going. So that's the mouth of Sydney Harbor. Sydney Mines in the foreground, New Waterford off there in the background. So in terms, this is the major sedimentary bedrock of the Sydney coal field. That's what we're going to be looking at in terms of water levels. So one of the ways hydrogeologists get a handle on whether the storage of groundwater is going up or going down is we look at the water level in wells at the end of the water year, the end of September. We compare it to what happened the previous year. And what you can see here is that sometimes it's low and sometimes it's high, but it's pretty much bouncing around against zero change. So in the deep groundwaters, that storage of groundwater in there seems to be remaining relatively constant on a year-to-year basis. But what's also important is seasonal changes. So this is similar deep groundwater well. And you can see in about 2007 onwards, we're getting really deep, lower levels in the summer. But thank God we get the fall rains and the whole thing recharges and it goes back up again. But if you've got a well, even if it's a deep well, we're starting to get these deep summer recessions going on. And perhaps your well might go dry because of those. So Nova Scotia Environment has 6 observation wells of deep groundwaters on the island. But unlike the surface water flow in the Northeast Margarita showed you, which is right up to present, you can get it just by clicking on the web. Today I just checked, but all of the 6 records for 2024 is the red line, stops in around May. So we don't know what's going on right now. The blue line is the maximum that's been recorded at that well. The yellow line is the lowest. But if we're going to try and make decisions, or if people are getting their wells dry and they're wondering what's going on, it's sort of like to be able to have this data, but it's just not kept up to real-time data as yet. How about shallow sedimentary bedrock? So we've got 2 wells in there, fairly shallow. So these would represent people that have shallow wells, dug wells, or working off of springs. Overall, the amount of storage in there seems to be the same from year to year. But what you'll find, the red line is a well that's in a top of a hill. The blue line is one that's down in a valley. So you can see if your well is shallow and it's in the top of a hill, you're getting a tremendous range of water level fluctuations, especially the deep ones. So if you're starting to run into problems, you have shallow wells, you're in a high area, you might be experiencing more changes than normal. Well, how about groundwater in wetlands? We had talked a bit about the wetlands previously, how important they are. So this is one of our research sites up in the Cape Breton Highlands. So we have 4 monitoring wells in there that we monitor. And one of the things we're looking for is the wetland drying out? The reason for that is that the big concern now is that if normally the water table should be really high in the wetlands, but if they start to dry out and the water table drops, then the bogs start releasing more CO2 and methane, which are greenhouse gas emissions. So this becomes important. So for that, I decided we take a look at the water levels we recorded from 2010 to present. So those lines are the depth of water below ground surface. And as you can see, they haven't changed. They're all running about 0.1 to 0.3 meters below ground. So as yet, we're not in any troubles. They're staying nice and wet. So that's a good sign. Well, groundwater is also important in terms of how it interacts with stream and maintains those low flows. So those have become really important in the areas identified in sort of turquoise there. That's where big, thick sand and gravel sequences are adjacent to the stream. And we want to know if the groundwater in those sand and gravels are still maintaining low stream flows. So we'll take you to this spot. So Dr. Jim Folds, who used to teach here, is an aquatic ecologist. He and I have been working for 20 plus years on developing a salmon management plan at Glenbrook. So we've got a lot of monitoring data in here. So if we plot up the head level, so this is a shallow well close to the stream, and these are how the head levels have been bouncing up and down. We also have one that's deep, because when you're in a groundwater flow system, unlike surface water, you think it's just flowing downhill. In groundwater, some of it's flowing downhill, but there's also a vertical gradient, which sometimes can be down and sometimes can be up. So fortunately, we have a deep one there. So you can see that the head level in the deeper one is higher than the shallow one, which means we've got an upward vertical flow. But how does that interact with the stream? Well, the green is the stage level in the stream. So you can see most of the time, even the blue, but always the red, are higher than the stream. So that means groundwater is going into the stream, which is called an effluent condition. The odd time in big stage levels in the stream and flood events sometimes goes above the shallow one, which means the water in the brook is going down into the groundwater flow system. And that's an influent condition. But over this period of time, we haven't noticed any big change. So that's another good thing. Now we come to groundwater, saltwater intrusion. So here are all the water wells. There are 14,886 well logs on the island. 55% of them are within 1 kilometer of the coast. So we have a bit of addition here that we have to watch out for. We have one well that we've been monitoring with a data logger from 1994 right up to present. This one just goes up to 2021. And you can see that the water levels are increasing, and they almost match. If you inserted the tidal levels on here, you would see there's a pretty close match to them. What is interesting though is that the sea level from the tidal stations indicated a 0.2 meter rise in 31 years. But this well, which is less than a half a kilometer from the coast, is showing a 1 meter rise in over 27 years. So one of the things you have to consider is that as salt water moves into coastal aquifers, because salt water has a total dissolved solids of about 35,000 milligrams per liter, and fresh groundwater would be like 200, 300, 400 milligrams per liter. Salt water is denser than fresh water, so it goes down and dives underneath the freshwater lens that's there. By so doing, depending upon the aquifer characteristics, it can push the freshwater head up above it. So sometimes people have basements that never flooded, and then all of a sudden they're wondering, what am I getting water in the basement for, even though the sea level isn't flooding my surface? So you have to, when you're getting into this saltwater intrusion thing, you have to remember that density impact, and flooding by surface water is one thing, but you can also get groundwater flooding because of the rise of the water table. Now we also measured to see whether or not there was any influence of saltwater in here. So you can see the red is total dissolved solids, and the two big chemical indicators of seawater are sodium, yellow, chloride, blue, or green. And so you can see for the first little while up through till about 2001, everything flatlined, but now we're starting to get not a gradual rise in these indicators, but pulses going through. So if you have a well close to the sea, you may not know salt water, or you may not see a saltiness in your water, but all of a sudden you'll turn the tap on one day and it's, oh, gee, where'd that come from? Well, it could be pulses of seawater coming into your well. So it's just something to keep in mind, that saltwater intrusion doesn't necessarily go in a nice linear fashion. So another aspect of saltwater intrusion into groundwater. We have to deal with Baechler ponds, of which we have over 1,100 along the coast and along the coastline of the Bedore Lakes. So what are Baechler ponds? Ooh, anybody got an idea where this one is? Ooh, got him stumped. So this is along the southeast coast of Cape Breton. If you're familiar with the Gabarouche Wilderness area, it's in the foreground there. And the first big embayment is called Belfry Lake. And then you're working back to the back part into around Framboise and Forshoe. So a Baechler pond is simply there's seawater, but the pond is generally fresh because these big barrier beaches are separating it from salt water. And so you get a lot of, you'll see in the right foreground here, you get a lot of people thinking, oh, these are a great spot to build a well, or build a house, drill a well, should get fresh water, because the embayment, in this case, Belfry Lake, is fresh. The way it sits right now is that the way salt water is going to get into these freshwater ponds is through infiltrating through groundwater into the Baechler ponds. But if the sediment dynamics that's creating those bars can't keep up with sea level rise, then they get inundated. And now those what were freshwater embayments are now saltwater. And some of the coastal geomorphologists with the Geological Survey of Canada have made some estimates that back when the sea level was 50 meters below where it is right now and glaciers receding, the rate of sea level rise was about 0.7 meters every 100 years. And that was fast enough to inundate a lot of these barrier beaches. So if you looked at the bathymetry inside the Bedore Lakes, you can see old river channels, you can see deltas, you can see old lakes, simply because they couldn't keep up with that rate of pace. As we've said right now, the rate of pace along the Cape Breton shoreline is about 0.36 meters, but the rate of change by 2040 to 2050 is estimated to be back in the 0.7 to 0.8 meter range, which means the viability of these bars is becoming a little bit tenuous. So it may be that some of these are going to get wiped out, in which case, if you have a well close to some of these what are now freshwater embayments, you may see seawater coming in. The other thing those barrier beaches form is a great protection against storm surge and wave height. So if you right now have your house along that inner shoreline, you don't have to worry too much about big wave action eroding your infrastructure. But to give you an idea of storm surge now, this is one of my monitoring points. So we'll take you to the beach here. So this is what Belfry Beach looks like at low tide. Hurricane Teddy, 5 meter storm surge, same spot. This is what it looks like. And you can tell from the vegetation on the left that it had overtopped that bar at one point. So if now all of a sudden these folks on the interior side of these Baechler ponds are open to this sort of storm surge, could be something that they have to keep into account. Okay, conclusions. Anybody know where this one is? Your final last shot at it.
In the geology book. Pillar Rock, it's called?
Pinnacle Rock.
Pinnacle Rock.
Oh, very good. So this is the Cape Breton Highlands Park, just north of Shinnecock on the west side of the island. Thought this would be an appropriate one, a good storm surge coming in. I've hit you with an awful lot in a short period of time. So I'll hit you with 3 takeaway messages. 1, climate, sea level are changing. Remember, there is human-induced changes, but don't forget about the natural rhythms and beats of our planet. So perhaps call it changing climate, not climate change. 2nd, surface waters are responding with changes in flow patterns, temperature, pH. Just keep in mind, because of all this new data we're collecting, add a lot more detail, when you start seeing changes, it may be just simply because we've got a lot more data and it's always been there. Finally, deep groundwaters are not showing as much response to surface waters. Shallow groundwater is a bit more so, and saltwater intrusion is becoming an issue. Alrighty, that should do it. Thank you very much, folks, for your time this evening.
Have any questions for Fred at CBU
Oh, good, no questions. Okay, I'm out of here.
before?
I have one.
Yeah.
Okay, so you're talking about our, like, precipitation stuff depends on where the jet stream is in that big oscillation pattern. And I've read stuff about like the big patterns of like the deep water currents and stuff, and how climate change might change those or like change the energy regime and make
Yes.
them less strong.
Mhm.
Is that something that's like, because we've also been hearing about polar vortices and things like that. Is that something that is also going to affect like where that jet stream ends up every year, or is that part of the natural
That'd be more a question for the climatologists.
thing?
But you raised a really interesting issue, because all the talk about changing climates is the world is going to get warmer and hotter.
Mhm.
And to a large measure, agreed. But in the North Atlantic, things could be a bit different, because we here on the northeastern side of North America, and Europe might go exactly the opposite. And the reason that that concept is there is, I talked about wetlands. People hear a lot about wetlands. What they don't realize is that wetlands are a living library of climate and forest cover. So you can take a core through them and you can see what pollen was at what level. There's carbon there, so you can do carbon-14 dating. So when they looked at the wetlands across the eastern part of North America, what they found was, as the ice left, the forest started growing in, coming in, tundra going to boreal vegetation. But then all of a sudden, boom, it went right back to tundra again, really cold. And that was, the first one was called the Younger Dryas. I think it was 12 to 13,000, somewhere around there, years ago. Then we climbed out of that. And then the next one, called the pre-boreal oscillation, we dropped down again. And then we climbed out of that. And then another one at 8,000 years, we dropped down and came back out of it. What they've done, though, is they figured out why that happened. And the reason is that although the big continental ice sheet was melting gradually and retreating, there were 3 big events where a massive amount of fresh, cold water got released into the North Atlantic and shut down those systems you were talking about. If you bring that forward to what's going on right now, the Greenland ice sheet is melting a lot faster than the International Panel on Climate Change has said. And it's pumping a lot of fresh, cold water into the North Atlantic. So that's certainly one of the big concerns, and they have all sorts of monitoring. Bruce could talk more about that than I could, about out of the North Atlantic to see whether that's really enough to create one of these impacts or not. But if it is, our wetlands have shown us what could have happened. I don't know, Bruce, any more on that?
Yeah, I mean, the current thinking is that we are getting closer and closer to a decrease in the injection of new water into the deep thermal halide circulation. And that absolutely will change the pattern of the North Atlantic oscillation and global patterns. Right. But that's a very slow moving train. You refer to the right one, which is, even though the ocean atmosphere system is warming globally, and certainly here too, and we have experienced particularly rapid surface sea level and even mid-sea level sea depth temperature increases, as the Arctic ice sheet melts and the Greenland ice sheet calves glaciers into the ocean, we could actually come into a time when our waters cool in comparison until all the ice is gone. And, you know, it's something that shorter term, people are looking at how lobster fisheries are declining to the south of us and increasing as they move northward. And lobsters respond as a good indicator of shallow water ocean temperatures. They don't live in really deep water. And we may get a bit of a respite from that because of the timing of the melting of the ice. So it's really hard to predict.
Right.
But I had a question. I was very interested in the really good relationships you were able to show between how water moves in the atmosphere or in the air and then on the surface. But now, because of some of this good data, you're able to really show the links to groundwater, or at least what you call the shallow groundwater.
Right.
And and so I've always been, had a very hard time thinking about how precipitation is reflected in groundwater tables. In the understanding that you have now, are you better able to predict the timing and magnitude of submarine groundwater discharges in those situations that aren't like our Baechler ponds, but where you have really big towers of groundwater, and it has enough pressure to push out underneath the sea?
Really good question. As usual, one of the really interesting things about Cape Breton is it has so many different hydrogeological settings because we have such a wide variety of geology. So what you might say for one situation might not apply. So some of the discussions we've had, like we have fault aquifers. Well, do they extend out into the ocean? We have karst systems. Do they extend out in there? And all of those, yeah, they're all taking place. So even if I thought I had a good idea, well, actually, one of the big unknowns we have is, so Bruce and I have been looking for some of these submarine groundwater discharge zones in the Bredor. We think we found one off of Iona, but we really need a lot more data on what's pumping that out and what's going there and what's the chemistry. Is it really deep groundwater, like 2/3 or twice the salinity of the ocean, or is it something else? So it's a really interesting question that I don't have an answer for right now.
Thank you. Great talk, Fred.
Thank you.
As always.
Any other questions? There are no, I don't think there are any questions online, so.
Whoa, it's beer time. Yes, all right.
Yes, that is everything. Thank
Good.
you so much.
All right, very good.
Good talk, Fred.
A question.
Oh,
Oh.
you might have one.
Hello.
Good talk from Roger.
Thanks.